Test. Okay, for those listening online, can you type a yes if you can hear me? Okay, thank you. Okay, let's get started. All right, let's finish the scalar line integral, and then we'll get on new topic, which is multivariable function. Scalar line integral, just a very quick review, is that if you have a curve, C defined by a parametric equation R of t. Okay. And then given a function f x, y, z defined over C, then the vector line integral is that you integrate this function f over the given curve C. So this is essentially what scalar line integral is. And there's a little bit different format in terms of the writing of the formula, but that's okay, right? So you should know that. Okay. Now, there's only one part of the things I need to cover before we cover that. So, but I wanted to maybe go into this scalar line integral a little bit more to give you a little bit more in-depth understanding of this scalar line integral. Okay. Yeah. So if you look at the current writing here, right? Look, the current writing, the C here is a 3D curve. So for the current formula I write here, so it's 3D. 3D basically means you pick a point on the curve and you have a point, you have a coordinate, which is x, y, z. Okay. And then you plug in this x, y, z into the function f, and then you give your value. And that's what we call this function is defined over this curve C. And then you integrate this over the whole curve C, you get a certain final results, right? So in the derivation of this scalar line integral, and we mentioned that now you could consider the f at here as a density function, then the result of this give you a total mass of this thin wire at here. Right? So that's one application of the scalar line integral. Now I want you to look at it. Let's look at the case of a 2D case. Okay, so let's say if I have a 2D case, how I can interpret this. Okay. So in 2D basically means the C is in XY plane. Okay, so then I'm still going to draw this in a 3D sense. Okay. So C probably will look like this. That's 2D, right, in XY plane. So this is a 2D curve. Okay. Then the corresponding scalar line integral, right, would be basically now you say, okay, because this is a 2D, then given instead of x, y, z, then we'll see, let's say, given a function f of x, y, defined over C. Right? And then you integrate this function f, x, y over this curve C to give you a scalar line integral. So far, everything is just downgrade one variable, right? And you can still consider this f as a density function. Then you get the total mass of this thin wire C at here. Okay, so now I want you to give you a different perspective, okay? Yeah. So the different perspective is this. And this is actually kind of related to what we're going to cover today in multivariable function. Basically, currently, I mean, this or either this, they all what we call multivariable function. And this f of x, y at here, and so in this particular case, when you look at just this function, okay, when you look at just this one here, as you're going to show it today, it gives you a surface graph in 3D space. So this guy here, depends on what the function is, you end up with just a surface. Okay, yeah. So now let's get back to this scalar line integral. Your scalar line integral is about integrating over the curve C, right? C here, meaning you don't care about anywhere else other than the points on the curve C. So if I pick a point at here, okay, then I substitute the coordinate at this point into this function f. Then you plug in 1 or 2, you calculate, you got a z value. So then let's suppose you get it somewhere here, right? And then you plug in another second value here, and then maybe you get another one. You plug in every different point, okay? So you give it different point. So basically you can imagine, right, as you're doing this one by one, and you get a number of points in the 3D space right on top of this curve C. That makes sense, right? So then you can connect all of the points, okay? You can connect all of the points, which is the results of every point on the curve C. Or in other words, is a result as you're integrating over this curve C. Okay? So now I have a green curve at here. And this green curve is a direct result of x is y over C. Good. So how is that going to help us when you think about it, right? So you're integrating this function over C. Basically, you're integrating what? You're integrating this green curve over this curve C, right? Because you're restricted to the curve C, okay? Even though this function is a surface, okay? So now you can see if I take a ds, okay, let's see if I take a ds at here, which is representing a very small segment of arc length, right? And then at this location, you got a height, and this height is represented by a value of, let's say, xk, yk, for example. Okay, yeah. So technically, what I could do, I could construct a very, very small rectangle at that location. So at this location, you got a f of x, k, y, k, and multiply by, let's call it, instead of ds, let's call it delta s, okay? Yeah. So you can construct a rectangle, and you multiply the value of this with the little bit of arc length delta s. And that's what happens here, right? You have f multiplied by ds. Of course, I'm enlarging a little bit, and this is delta s. Okay. So what is this multiplied by delta s? When you multiply the height with the base length, you get what? You get the area of this little rectangle, right? So if I keep doing this along the curve C, I have many, many small rectangular box, and then I add up, right? Basically, integral is basically means that you add up all of these small areas. So what do you think this actually give us? Go ahead. Yeah. The what? Sorry. A plane? No, it doesn't give you a plane, right? So individually, it gives you a little bit of area here. You're adding up all of the areas. You're adding up all of the areas underneath this curve. Does that make sense? Then in total, this is basically integral here. In total, then you get what? The surface area, exactly. All the area underneath this curve, above the curve C. If you consider this is a curtain, And this curtain, the top of the curtain is defined by the function f, of course restricted by the curve C. And the bottom of the curtain is given by the curve C. Then this scalar line integral essentially gives you the area underneath f of x, y, but above curve C. So that's a different perspective on the, with respect to this scalar line integral. Yes. The height here? The height is determined by this function f, right? So as I said, if I pick a point right here, let's say this point is xk, yk, then you go up to the curve, okay, just go up to the function f, you get a value f of xk, yk, and that basically is the height of this little box here, right? Still a little confusion, yeah? So you gotta understand how the top green curve is generated. How is this green curve generated? It's generated based on the function f and the curve C. You pick a point from the curve C, you plug it into this function, and you get a point on top of the curve C, or the bottom, right? Doesn't matter where. Okay. And then you collect another point, you get this green curve here, or the top of the curtain. Okay. So that's how you can interpret. So you can only interpret this for a 2D case. If in a 3D, like this, you know, here you have f of x, y, z. 3-dimension restrict us, we cannot plot f of x, y, z. If you create another dimension, then you can. Okay. But in this case, we can't imagine where is the f of, well, it's just a value, right? But you cannot plot it anymore in the x, y, z 3D space. Okay. Okay. So either way, you know, there's different basically understanding. That's the beauty of math, right? You put down a formula, you can actually understand it from different perspectives, right? Okay. So let's look at the last point of this scalar line integral, which is not that difficult to understand. It's actually quite straightforward. Is that we need to talk about one property, okay, for vector line for the scalar line integral. Okay. And this property is called additive property. Okay. So additive property basically means if the curve C consists of multiple segments of curves. So let's say C1, C2, and maybe even n number curves. So what it means is when you integrate over curve C, then you find out the curve C actually, right, consists of so many different segments of curves. Each segment is represented maybe by one parametric equation, right? Then in this case, if you're required to integrate this function over the curve C, then you can apply this so-called additive property. So you essentially you do a piecewise integral. So very much like a piecewise integration of scalar function. Okay. So from A to B, B to C, C to D, right, until you end up you complete the integral, right, from within the range. So that essentially is what I wanted to point out here, because this is actually kind of useful property. So let me show you an example. I'll use an example that when we learned the parameterizing curves, okay, we had this example. Essentially, we have 3 points given in 3D space. And then we create two curves called C1 and C2. And now I'm giving a function f of x, y, z equal to x plus 3y squared plus z. Okay. And we want to integrate this function over C, and then C equal to C1 plus C2. There are two segments to form the curve C. Okay. So as clearly says, because C is C1 plus C2, so then what you need to do is, right, you need to calculate two line integrals. One is over C1 and the other is over C2. And then you add them together. Okay, so for this kind of question, this is another time I'd emphasize you got to be able to write down the parametric equation for simple curves like this. Okay, simple means they're just essentially a straight line, and they're connecting 2 points in 3D space. Then what are the parametric equation candidates, right? So first step, you had to write down the parametric equation for C1, C2. Again, there are no set answers, right? There are infinite solutions you could provide, but typically you maybe choose the easiest one here. So C1, I will use T0 as we did in our exercise. T goes from 0 to 1. Okay, so that will give me the C1 curve. For C2, it goes from 110 to 111. So x and y coordinates is not changing. So 1 and 1 for x and y coordinate, and z go from 0 to 1. So I choose a t representing the z change. The t again goes from 0 to 1. And that's our choice when we did the example in the lecture. But of course, as I said, you can certainly come up with a different parametric equation. But then the limits for the t, right, will change accordingly. Okay, so once you get this step, and then the rest of them is, again, it's apply the formulas for scalar line integral, but you do need to calculate separately. So let's say for C1, we're integrating over C1. So fxyz ds. Now it's time to manipulate this formula. And if you recall how we do that is we replace x with x over t. We replace y with y of t, and then replace z with z of t. At the same time, ds is dr1 over dt dot dr1 over dt and dt. Okay, so let's see how we're gonna, what will be the results of the manipulation. Your function f is given over here. So time to do the game of replacement. I'm gonna replace, this is x of t, y of t, z of t. So I'm going to replace x of t over here, y of t over there, z of t over there. So this whole thing with the replacement, so t plus 3t squared plus 0. And the derivative of the vector function is 110 dot 110 dt. And t going from 0 to 1. Okay, so up to this, I think the rest of the work is, oh, sorry, did I, this is minus or plus? Oh, this is minus, sorry. I use a minus here, but that's okay. Yeah. I mean, my lecture notes minus. This is minus here. All right, so I think you can calculate this one here. You get a negative √2 over 2 if you carry out the rest of the calculation. So that's integral results for C1, right? So then you do the C2. So C2 t also go from 0 to 1. So how am I going to substitute? I'm going to substitute 1 over here, and then t over there. So 1 minus 3 plus t, and that's negative 2 plus t. So we get negative 2 plus t at here. And derivative 1 0 0 1 dot 0 0 1. And then you get negative 3 over 2. Okay, so then you add them up. So overall integral, right, over this c and equal to negative √2 over 2 minus 3 over 2. So that's piecewise curves and calculate separately and then add them up. Right? So there's really no trick at all, right? Only trick, typically, the only trick is first step, get the parametric equation correctly for each segment of the curve. Good. Okay. So that's pretty much about the scalar line integral. Okay, so in the later part of the lecture, we have another one called vector line integral, but we'll come to that. Okay. Yeah. So before I end, let me end up with this lecture with a very simple quiz kind of things. Okay. Okay, so let's see if you can answer this multiple choice question correctly. So here's a question. Consider this scalar line integral formula. And then we have 3 questions here. Which one of the statement is false? First one, function f is defined over curve C. Second one, curve C can consist of multiple smooth curves. The last one, the linear integral of this f over the smooth curve C depends on the orientation of the curve. Okay. So if you got a clicker, then you can select it. Anyway. So let me see who think the A is false. Okay, good. Who think B is false? Good. Who thinks C is false? Excellent. Okay, good. So I think we specifically mentioned in the lecture, this scalar line integral does not depend on the orientation of the curve C. Okay. By orientation, basically means you go from one side to the other side or from the other side to this side. That's orientation. Right? Okay. Good. Even piecewise scalar line integral, let's say C1, C2, C3, right? Now, as you can see in this question here, when I integrate over C, my t goes from 0 to 1. When I integrate C2, my t is reset from 0 to 1. Right? It's fine. Now, if you want to say, okay, can I say t 0 to 1, and then somehow I let the t from 1 to 2, for example, right? That's like a continuous change of time t, which is fine. But of course, your parametric equation probably will have to change, and most probably in this case it will change, right? If let's say if your t, you want the t to go from 1 to 2, then the t here will actually be what? If this is 1 to 2. And you impose 1 to 2 basically. So what would be the choice for the z quantity? Okay. T over 2? No. So you got to make sure when t equal to 1, your coordinates is 0, 0, is 1, 1, 0. So what would be the candidate here? T minus 1. Good. Okay. So that's my point here, right? And you can try this and you should get exactly the same result. Okay. Okay. I think we're all good. So now let's get away from the vector field or vector functions or vectors in general. Let's get back to a topic, function of multivariables. And the reason we're going to do this part is because we're going to talk about integrals over surfaces. We're going to talk about many other things related to multivariable functions. But multivariable function, right? We have already dealt with them. Okay. So, and we also have to talk about its calculus. Okay. So how do we calculate derivatives of a multivariable function? And how do we calculate integrals of a multivariable function? Okay. So as you can imagine, if a scalar function, when you do integral, you just integrate a to b with respect to the variable, say x, right? But if you have a function of multivariables, x, y, z, or just x, y even, then I cannot just do one integral anymore. I had to do multiple integrals. So that's what we're going to end up with, double integral and triple integral, right? Associated with a multivariable function. Okay. But for starters, what I wanted to is to give you some basic sense of what multivariable function actually looks like. Okay. And we establish a sense of visualizing multivariable simple ones, just function of two variables, giving a very simple function so that we can graph it and then we can actually do something with it. All right, multivariable function will look like this, which we all have already known. You have function two variables. If you have function three variables, okay, so then you write it, right? Instead of z here, you define new variable w. And those are multivariable function. And you can certainly define yourself a very general multivariable function. Now there are n number of multivariables, right? Variables here in this function. And just like scalar function, anything within the bracket is called independent variables. And anything that's outside, the one on the left side here, is called a dependent variable. Okay. So where do you see a multivariable function? You know, very, very common. So let's say, for example, you're talking about the temperature inside this room. So you pick a point inside the room, which you use the coordinates x, y, z representing the point, and you plug in this function, then you get a temperature, right, at that point. And you climb the mountain, right, and you plug in x, y, z, then you got an x altitude of the mountain, right? But that's going to be a function two variables, right? So as I mentioned, I want to show you some graphical examples, okay, for function of two variables. Basically, this type of function. Now you might wonder, how come you only show me graphical example for function two variables? How come you don't show me a function graphical illustration of function of three variables? The reason is you can't, right? Because we're restricting a 3D dimension as human being, and we can only, I mean, typically not a computer can help you visualize multi-dimension, but in reality, when we think about things, we're restricted to 3D basically dimension, right? So when you have a 2D, when you have a function two variables, okay, and so for example, you give a point x, y, you got a z, you give a different x, y, you got another z, and when you connect all the points together, you got a surface, okay, you got a curve. But if a function three variables, then you can't do that anymore, right? That's what we call the restriction of of a 2D, three dimension. All right, so let's take a look at what are the typical functions I want you to familiarize yourself with. So let's say I have this simple function, z equal to negative y. So even though I said this function two variable, and then in this example, there's only one variable y showed up here. Okay. And z equal to xy. Now, if I ask you, y equal to x, you probably everybody know, okay, that's a straight line, right? Yeah. But of course, this time it's z equal to negative 1. So technically speaking, if you plot this, okay, if you plot this in the zy plane, and then you get a straight line, right? You get a straight line in the zy plane. So z equal to negative y itself means it's a straight line. However, if we put it in a 3D perspective, then z equal to negative y basically means you expand, right, that line, okay, the left and right or front end, okay. So then you get a plane in this case. So you extend the line, right, you get a plane. So this one here, next time when something jumps to your head, so let's say, for example, what does y equal to 2x plus 3 plus 3 looks like? It's a line in 2D, but in 3D it becomes a plane. Right? That's what I want you to establish this concept here. Okay, so this one is fairly straightforward. Now you can also actually think this way. Remember when we learn planes, the general plane equation. So let me move this down a little bit. The general plane equation is what? Is ax plus by plus cz equal to d. Right? That's a general plane equation. So we never say what ABC has to be, but so if you set a equal to 0 and you set d equal to 0, then you get the current z, and of course you set b equal to 1 and c equal to 1, then you get z equal to negative y. Right? So z equal to negative y essentially is a special case of the plane equation that we have demonstrated. All right, let's take a look at the second type of surface, which is this one. So z equal to 1 minus x squared minus y squared. So this one, if you plot it out, it will look like this one, like this. Okay, look like this. Now, there's a bit of a different way you can also try to visualize this. Okay, so this kind of curve is called, okay, as I said, it's listed here, called elliptic paraboloid. Okay. I think it should be pronounced paraboloid. Okay, elliptic paraboloid. Sometimes just call it paraboloid. Okay. So you look at this function here. I mean, if I ask you a question, can you tell me what is the maximum value for z? What is the maximum value for z? Exactly, 1, right? Because this is x squared is positive, always positive. Y squared is always positive. So 1 minus 2 positive. Your maximum you can get is 1, right? So that can help you actually visualize the shape of this paraboloid. It's a paraboloid goes downwards, right? Yeah. So let's say, for example, if I give you a different function, let's say z equal to x squared plus y squared. So this one is certainly different, but if I use a similar thinking, if I know this is a paraboloid and this is what it looks like for a paraboloid, then how would this z equal to x squared plus y squared look like? What would be a critical point? The z must have a minimum point, which is at The minimum value for Z is not two, minimum value is what? 0, right? So it cannot go below 0. So minimum is 0, and then you can certainly sketch that and by drawing a paraboloid pointing up. Okay. So that's what I want you to be able to do, huh? Yeah. Yes. Is that a reflection of what? Of this one here? And not necessarily, no, not really, because this one here is 1, right? This is 1 here. So if I plot both on the same graph, then for this one here, if this is 1, then it goes down, right? It's not really. If I ask you what is the reflection of this one, the reflection of that one should be what? You just put a negative there, right? Negative x squared plus minus y squared. Right? Then it's going down, right? Downwards. Yeah. Okay. So my expectation is, we're going to deal with this kind of paraboloid actually quite a lot in many following examples. So if any questions coming up with this functions with this kind of geometry or format, then you should be able to plot it, because let me tell you, plot it out will help you so much in understanding the question, right? So you don't have to plot it very nicely like what I did here. I think that should be enough, right? To help you visualize the question, understand the question. Okay, another thing is, we'll come to that when we talk about contour, right? So let's say, for example, either one of this, let's pick either one of this here. So if I have a z equal to x squared, y squared, for example, so this paraboloid, okay? Yeah. And then if I let z equal to a constant c. So basically the green color one, right, is the blue one is this paraboloid. And now I'm letting z equal to c. So, and if I ask you, can you solve this? What do? You basically plug in c over here, you get x squared plus y squared equal to c, right? Okay. So what's this? It's a circle, right? So when you look at this one, a circle, but so certainly, okay, this is a circle, you draw it. But however, this circle is not in the xy plane. This circle is at which location? At z equal to c location. So basically, you need to find the c value of the z, and then you draw a circle, okay, at that location. So that circle is the cross section right here. Okay. As we're going to learn next, when we see z equal to c, you can also interpret it, not just z is a constant. You can interpret z equal to c as, what can you interpret as a what kind of entity can you interpret z equal to c as? Is it a line? Is it a dot? Or is it a plane? Right? Exactly. So you can interpret it as a plane here. So this is z equal to c. And that plane, this is a plane, and that plane intersect this paraboloid, presenting you with a circle, which is this. So if you change the c value, you get a different circle. Right? So this paraboloid basically is a whole bunch of circles, right, on top of each other. And later we're going to learn, we actually call this is so-called contour. You could a contour, cluster of contours for the current surface. Okay. Okay, so that's the second example. Okay, and let's look at this example here. Z equal to x squared minus y squared. So this function is x squared, not x squared plus y squared anymore. It's x squared minus y squared. Right? So if I plot it out, it looks like this. So what does this surface remind you? What kind of a geometry does it remind you? Right? I think it says here, it's a saddle, right? It's like the horse saddle. Okay. Now, the thing about saddle is, if you are somewhere situated here, right in the middle of the saddle, and if you start walking in this direction, okay, you start walking this direction, basically you're going downhill, right? But if you go this way, then you're going uphill. So this point, what we call is a saddle point. Why is it called a saddle point? Because typically, when you go from one location, you go to a direction, you might be actually, doesn't matter which direction you probably will go down, right? But then in another case, you probably will always go up. But in this case, for this particular surface, so unfortunately, you cannot tell. You have one direction going up, and then you have one direction actually going down. That's called a saddle point. So when we learn so-called extreme points or mean value, maximum value associated with the surface, right? And unfortunately, the saddle point is not part of that. So you cannot tell you cannot say this is a minimum point or maximum point at all, right? Because it's a saddle point. Okay? It can't be a mean and a max at the same time, basically. Okay, so that's this one, all right? So if the next time you see some functions of like a 3x squared minus 2y squared, so it's essentially still a saddle surface. Okay. All right, so the next one I'm gonna write it down for you. Okay, so this is example, let's see, 4. And this one I'll present it to you is a little bit longer expression. Okay. Whole bunch of variables, squares, cubic terms, right? Stack them together, okay, you get this equation. Okay. And this equation, if you look at the orders, this is x2 to the power 2, and this is to the power 3. So maximum order 2 to the power 2, 2 times 3, you get 6, right? So this is called a sextic equation, okay? Sextic equation. Now, what does this equation look like if you plot it out? Give your hearts, okay? And you can massage this a little bit, actually you can get a slightly different shape of heart. But anyway, so you get a heart out of this sextic equation. It's a beautiful heart. Try the mathematical code yourself. You can plot it out. Okay, that's amazing, right? You know, this seemingly random function at here, okay, is showing you as a beautiful heart. So somebody actually, I forgot a name, who find this equation here, and there is an alternative equation. Also, you can plot it out as a heart. Okay. Now, maybe I'll just take a snapshot and put it into the. Okay. So let's go back to this equation. All right. Let's talk a little bit about this equation, and hopefully you can find some different. What is the difference between this equation and this kind of equation, or this equation, or this equation? Okay. Or this one, okay, doesn't matter. The difference, if you look at it, is that for any one of the equations, multivariable functions, okay, that listed here, here, you have z equal to the function. Okay, you have explicitly given, you're explicitly given what is the function for the z. That makes sense, right? So this thing here, basically those things, we call them explicit function. Okay. Because the expression for z is showing, But this one here, right? This one here, you look at this, I don't have a z function given. And it's embedded, it's hidden, right, within this left side at here. So for this type of thing, we call it implicit function. Because it's implicitly given. Another example of the implicit function is x squared plus y squared plus z squared equal to, for example, 8. And this is another example of implicit function. And I think you probably know what this looks. What's x squared plus y squared plus z squared equal to 8 actually look like? It's a sphere, exactly, right? You know, x squared plus y squared is a circle. And then you add a z squared here, you got a sphere. Okay, it's a spherical surface. So as you can see, this is also an implicit function here, right? Sometimes you can transform implicit into an explicit, but sometimes it's very hard, especially like this one here. Right? So functions, another thing is called sextic equation. I mean, if just for your own reference, when you have an equation, you know, the first one is typically called a linear, and then you can have a quadratic, right? Order of 2, right? Linear is order of 1, and then you can have a cubic, that's order of 3, and the order of 4 is you have a quadic, right? And then 5 is a quintic, and 6 is what we have so far, and the 8 septic, as you go on and on. Okay, yeah. So that's how you can call this type of equation here. All right. Okay. So you're not going to have too sophisticated equation, okay, or surface. For this course, I want you to basically be able to visualize simple surfaces like a plane and paraboloid, okay. Sometimes it means spherical. Okay, so that should be enough to deal with all the rest of the questions, okay, to visualize in terms of visualization. All right. Any questions on this part of multivariable function visualization, graphical example? Okay, we're good. All right. So now let's quickly look at another another topic. Okay. And I have touched upon it a little bit already. Okay. It's called a contour plot, okay, for function of two variables. Okay. So I might not be able to get on to the details here, but let's just consider the idea here, and then I'll show you some examples. So let's say this is a function of two variables. Okay. And what we want is, right, we want to visualize it. So we just showed you, you know, you have a function, two variables, you can certainly graph it out and then present yourself with a surface. Right. So that's one way to visualize this surface. And you plot it in a 3D space. So what would be an alternative way then to visualize it? And the alternative way is this so-called contour plot. Okay. So the contour plot, you need to basically create this plot. Okay. Okay. How do I create this contour plot? So the way you can create a contour plot is you use the plane z equal to c. Then you are going to slice the surface z equal to f of xy. You don't just slice once, you slice it as many times you want by setting the C to different values. Because Z equal to C is a plane, so whenever you slice it with the plane with the original surface, you get a curve, right? And then you drop all of the curve into XY plane, right? So technically you have the curves in 3D space, but you drop all of the curve into the XY plane. And that cluster of a curve is called contour plots. Okay, so I'll stop here and we'll touch this in more detail in the next lecture.